Hello guys, welcome back to Calculus Universalis, and today we're going to be going over slope fields. These allow us to graphically represent solutions to differential equations without actually solving them. Today you'll learn how to construct a slope field, interpret a slope field, and match slope fields to differentials, a common AP question. So, let's go ahead. What is a slope field? A slope field is a tiny grid of mathematical slopes and tiny tangent line segments. So it's going to look something like, just wait, this. So you'll have something like this, and at each little line is going to be a slope, and the slopes will often get steeper and represent what the slope is at a singular point. So it's going to be like this. So 1, 1, it'll be 1, maybe at 2, 2, it's 2. So this basically just represents the graph, and at a certain point, that's what the slope is, and it represents it on here. So, let's go ahead and hop into some examples. So if we have a function dy over dx equals x minus y, then at the point 2, 1, the slope is 1. Right? Each segment gives a snapshot of the slope of the actual solution that you would have at each point. Now, why are these useful? They help you better visualize the behavior of a differential equation solutions. They're useful when the equation is too hard to solve algebraically, and they can suggest what the solutions look like, either increasing, decreasing, or asymptotes. So how do we construct a slope field manually? So if you're given a differential like dy over dx equals f of x minus or x comma y, you're given a set of xy points like a grid. For each point, plug in the coordinate to f of x comma y and draw a small segment with corresponding slopes like this. And 1, 1 might be 1, 2, 2, it'll be maybe like negative. Let's do a real world example. So example number 1. We're going to draw a slope field for dy over dx equals y at these points, negative 1, negative 1, negative 1, 0, negative 1, 1, 0, negative 1, 0, 0, and 0, 1. So, to do this, we'll draw a grid and plug in. So, we'll start with negative 1, negative 1. So if you plug in all your points, there's no x value, so you just plug in the y. It's going to be negative 1. So negative 1, negative 1, which is going to be a slope of 1, right? Negative 1, 0, it's going to be slope of 0. At negative 1, 1, up here, it's going to be a slope of 1. At 0, negative 1, Down here, it's going to be -1. And 0, 0, it's going to be 0 again. 0, 1, it's going to be 1. So that's your slope field. And this creates a pattern of increasing slopes as y increases. So, let's go into example number 2. Okay. What does the slope field of dy over dx equals x look like? Slopes depend on only x, not y in this equation. At every point with x equals 0, the slope equals 0, which is horizontal. At x equals 1, slope equals 1. At x equals -2, slope is going to be -2. So all vertical lines have the same slope pattern. Now example number 3. Suppose a slope field shows horizontal lines at y equals 0. At y equals 0, we're going to have a bunch of horizontal lines. Positive slopes above the x-axis, so something like this. Negative slopes below. Which equation fits best? dy over dx equals x equals y or equals x minus y. Which of these three matches this the best? Go ahead and pause and try to solve it yourself. Since the slope only changes with y, not x, eliminate a and c. So it's only going to be changing with y. So let's summarize what we learned today. To recap, slope fields are a way to visually show all possible slopes and solution curves to a differential equation. At each point, you can draw a small segment equal to dy over dx. Help predict solution behavior without solving. And they're tested on FRQs and multiple choice. So when the AP exam says draw a slope field, they want the correct slopes, not a perfect graph. Some practice problems you can do are sketching a slope field for dy over dx equals x plus y. Finding differential equations, how they match a slope field with horizontal tangents along y equals 0, and then describe how slopes can change as x increases. Next up in day 4, Euler's method. How to use slope field information to numerically approximate a solution curve. It's all about building a curve from a